Yeah. Whoever did that. Okay,
Nice
great.
job.
Oh,
And
I
we're
heard it.
recording. All right.
Nice.
Thanks, guys.
All righty. So is everybody seeing my continuing education AIA screen?
Yes, sir.
Fantastic. All right. So you guys know the blurbs. Again, I'm going to try not to be reading too many of these slides to you all. You can read. But I will be pulling up other couple of items as we go along. A couple for the camera, a couple for the screen share. So here we go. Maybe. Let's get that over here. And we move on. Okay. All right. Fundamentals of lighting. What? I pulled up the wrong PowerPoint. Hold on. That's what we did last time. Let's see here. I go here. Go photometry. Maybe. There we go. And then, sorry about the technical part here. Let's move. Okay. It's over there. That's right there. Let's see if I can pull that over here. Hold on. Yes, I want it. Oh, here we go. Ah. All right. Do you guys now see metrics, photometry, calculations, and rendering?
Yep.
Yes.
Fantastic. Now that I'm on the right section. All right, here we go. So when I started doing lighting back in college, when I went to my first lighting class, one of the things that almost overwhelmed me was the sheer number of ways to talk about light and its characteristics and how it interacts with physical space. Okay. So I want you all to relax. It's all good. We're going to explain every single one of them. But sometimes what I did when I went to class is I had a cheat sheet that described each and every one of these six key metrics that they start talking about here and how they related to the others. And that helped me a lot as time went on in class to figure out how things interacted with each other. So don't be intimidated. It's all right. You'll get through it. Right. That's my note to you all. Right. We're going to talk about photometry, photometric reports, ways to calculate stuff. Right. This is the geeky kind of thing. And I like it a lot. And anytime along the way, when you guys have questions, please ask, because I want to make sure you understand the concepts behind some of this stuff. Some of these slides don't go deep enough, so I'm going to go a little deeper. Some of these slides have some incorrect information on them, so I'm going to correct it. But we're going to talk about all those things. All right, here we go. So, photometry. How do we describe light as it affects people? Right? That's what photometry is, because there are two different parts of this thing. You can measure the electronic output or electronic output. You can measure the output of light sources across the spectrum and show that on a graph, right? How many watts or joules per second or whatever it is you want to describe them as are coming out of that light source at, say, particular wavelengths. However, and that describes the source very well. But what photometry does is it takes that information and it runs it through how we see light as people. Okay. So I believe back in an earlier iteration of stuff, you guys learned about the V lambda curve. And the V lambda curve is how people respond to these different wavelengths of light. It's a big bell curve in shape, right? And it peaks at green, like 555 nanometers. I don't know if any of you have noticed, but over time, construction workers are not wearing orange anymore. What color are they wearing? When you see guys at job sites and stuff, they're wearing
A
green,
lime green.
lime green. And the reason they wear lime green is because that is the, or near right? The peak of our sensitivity. So if you want somebody to be noticed, wear something that's at the color of what's the peak of our sensitivity, right? Not necessarily off to one side or the other. And also orange can have some issues with folks with color blindness. So the green vests are much more visible, and you'll see people in motorcycles with green stuff now. You'll see people on bicycles with green stuff now. It's because the clothing and protection industry is caught up to vision science, essentially, right? So that's a little bit of what photometry is. It's the interpretation of how a light puts out light according to wavelength, and then interpreted by that V lambda curve as to how people see, and that is also how we see during daylight hours. There are different things about let's call it twilight and the nighttime hours, but we're not going to go into that right now. All right, so we talked a little bit about that. Radiooptomy, that's what I talked about when you measure the output of the fixture across the spectrum. And then photometry is when we apply the V lambda curve to it. Now we understand how that thing puts out light for us to see as people. And here they are, right? This is what I had to make a cheat sheet for when I started going to class. Right? All these items about light that you need to understand. How can there be 6 or 8 different things involving light? Well, here they are, right? First of all, luminous flux. That is across the visual spectrum. How much energy is emitted, and then apply the V lambda curve to it. And we call those things lumens. How much output over, joules per second of this entire thing applied to the V lambda curve. That's called flux or lumens coming out of a fixture or something, right? So it's a quantity. You can think about it as droplets of light, right? It's a kind of simplified version of it, even though it's energy per second of that light coming through all these other things. But think about it as drops, right? So luminous flux, drops of light. And you can measure the light output of a fixture into how many lumens it puts out. And we talk about what's really cool nowadays. When I was growing up, when you bought a flashlight, you talked about what kind of batteries you put in it. Now you talk about how many lumens it puts out. Super nice, right? You actually know what that lamp is going to do for you. When you go to Costco and you buy the 4-pack of 1500 lumen flashlights, you know what they're going to do, and it's just awesome. That's lumens. Now, luminous intensity, and this is something that don't go into deep enough, but I'm going to go just a little bit more geeky on you, right? Is candela, is what they call it. And what that refers to is how many lumens, the drops we talked about, go into a cone that goes off into infinity, right? And the cone is called solid angle. So if you start at like the sun and you come out in a cone coming out from the sun, how many lumens are going into that cone, right? They're steady going into that cone, and that's its intensity. How many lumens per cone, if we want to talk about it that way? The real term is steradian, and there are 4 pi steradians in a sphere. They didn't give you that background here. It's very important to understand that stuff, right? So if you have lumens per steradian and you have 4 pi of those steradians, right? You have an intensity. If you put 1 lumen into that whole thing, you have an intensity of 1 over 4 pi. I don't know if I'm explaining that quite right yet. But if you put it into 1 steradian, lumen per steradian is called a candela. And there are okay, so that's it. A uniform source emitting 1 lumen per steradian has about 12 lumens to it, because there are 4 pi of these steradians in a complete sphere. So if you put 1 lumen into each of those, 4 times 3.14, blah, 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 right, is 12. So a source that puts out a lumen into all directions, right, into those 4 pi steradians, now you have a 12 lumen source. We'll come back to that and I'll explain it maybe a little more better later. All right, just wanted you guys to know about that 4 pi thing. Illuminance then takes those lumens and you drop them onto an area as you move out into one of those cones, right? You're into that one steradian cone. You put a lumen into it. That's an intensity of 1 candela, a lumen per steradian. I think that's what I was just missing, right? 1 lumen per steradian is a candela, and that's what they refer to as these terms of luminous intensity, right? If you get a foot away from that source, you still have a lumen per candela, but then the area that's subtended by that is about a foot squared. If you go out 2 feet, that cone keeps growing, but you still have the same lumen in it. So this explains why, as you go farther and farther and farther and farther away from a source of light, you get less and less light upon it because the lumens in that source are being spread out into that cone. And that cone, if you slice it, is getting bigger and bigger and bigger in terms of area. So a foot candle is a lumen per square foot. You drop one of those droplets of light onto a square foot, you have a foot candle. And that is what we measure the most is foot candles because it's easy to measure. It's easy to calculate, right? Um, so that's illuminance, which is next on this list, right? A lumen per foot squared. Now, we deal with Europeans a bit, and sometimes they'll take that same lumen, same radiant energy per unit time times the visual response curve, right? They'll take that same lumen and they'll drop it onto a meter squared instead of a foot squared. So the ratio of foot candles to lux, that's what they call it, dropping a lumen onto a square meter, is the ratio of the area of a square foot to a square meter, which is 10.76. So you will find some specifications sometimes for cameras or even government documents and things like that talking about how many lux you need on a project. Well, that lux is just a lumen per square meter, times it by roughly 10, okay, 10.76, and you get foot candles. So if they call for 500 lux, you're looking for 50 foot candles. Same thing in the reverse. If you're doing some business in Abu Dhabi and you want 50 foot candles in an office, you want to supply them with 500 foot candles. That's the difference in illuminance, right? Droplets of light onto an area. Reflectance. How many of those droplets bounce off? Right? Pretty easy, that one. If you have a fully reflective surface, be 100%. If you have a completely black absorbing surface, 0%. Most things are in between. Right? And then there are other characteristics to reflectance that again are sort of glossed over in here regarding how that reflectance functions. If you drop a laser onto a piece of tissue paper, I say that deliberately, tissue, and you walk around the tissue paper, it will look the same from every single angle. Do you know why that is? It's because it's a diffuse reflector. So when you drop any light onto a diffuse reflector, it bounces that light out into a sphere and you can see it from any angle that you go to. Now, take that same laser and instead of a piece of tissue paper, bounce it off a mirror. You might see a teensy bit of that laser come back to your eye at other angles because of dust or impurities in the glass or the silver reflector behind the glass on the mirror. But the vast majority, let's say all, bounces off at an angle equal to the incident angle to the mirror off into space. Right? That's called specular reflectance. So most real life scenarios, kind of a combination of both, right? You go into your bathroom and you paint it with a semi-gloss, and there's a bit of a sheen to it. So that particular paint now has two kinds of reflectance. It has a little bit of a specular, and you'll see it if you look at a 3D representation of how it bounces light. There's like a big punch that comes out at the equal angle to the incident, but then there's another sphere involved behind it where it also acts like a diffuse reflector and you get light coming back off of it. So you shine that same laser onto your bathroom wall, you'll probably still see a dot at an angle equal to the incident on the far wall from your laser, but you'll probably also see a much brighter little dot of the laser on the wall because it is sending some back to you as part of that diffuse reflectance. That's what comes into play in the next category here, luminous excitance. They are assuming a diffuse reflector to even invoke this concept of how many lumens per square foot are coming off of that surface. Right? Luminous excitance is diffuse light coming off of a surface in terms of either lumens per square foot or lumens per square meter. And then luminance, now we have to go back up to our candela per steradian and apply it to an area, right? How many candela, luminance per steradian, per square foot or per square meter then is the source sending to you, or is the surface that it's bouncing off of sending to you? So here's another thing, right? Illuminance is separate from the characteristics of the surface that it's illuminating. So for instance, my standing desk here is black. If my standing desk here were white, the light reaching that standing desk is the same. The illuminance value is, and I'm probably guessing about 10 foot candles. It's not very bright. But the light bouncing off of that surface is ridiculously different if I had a piece of white paper covering it or if I have my standard black desk, right? But what we see is light coming off of surfaces. So when you start to think about the visual environment, right? Surface characteristics mean a lot. You get folks who say, oh, well, I thought I lit this place to a good foot candle level, lumens per square foot, but I walk in there and it's dark. And you talk to them. You say, well, all right. If we bring a meter in, we'll check out and we'll see what you got on the floor. We'll probably find that we have, let's say it's a downlight in a corridor, right? You'll find they have plenty of light down on the ground. But the problem is that they have dark wood paneling on the walls. Well, of course it's dark. You have dark wood paneling on the walls. If you want to overlight the wood panel so that it looks good, that's fine. But you have plenty of foot candles on the ground to walk around. We're meeting guidelines. We have 10 or 12 or 15 foot candles, but the walls are dark because you painted them dark. That's why, right? People sometimes don't think about all those things, and they really do need to be taken into account when you try to track light bouncing around a room. And we'll be getting to that later in our presentation as well. So those are the 6 things. And, I encourage you to take a snapshot of it, keep them to the side, write them down somewhere because we'll switch back and forth between these numbers. And when you can understand how they relate to each other, it's very important. All right, this is kind of fun. Things about light that you can measure, right? Either about the source, the condition, the materials. We talked about reflectance down below. And this little chart here talks about all the different pieces of equipment that you could get to measure parts of your lighting system, whether it be the surfaces, the fixture, how they all interact with each other, how much light comes down to the ground, how bright something is with a luminance meter, right? And there's pictures of all these next. Here's somewhere along the way. I thought it was next. Maybe not. All right. There are photographs of these somewhere in this presentation, but the most common used device of anybody out there in the lighting world is an illuminance meter. How much light do we have reaching a particular surface, right? And you can obtain those in various and sundry ways through different catalogs with various and sundry different accuracies. For instance, if you're going to just be doing indoor lighting, if you're off by a foot candle on 50, it really doesn't matter. So that device can be a little less discerning, right? If you go outdoors and you are now talking about municipalities requiring you to be at 0.1 foot candles at a certain something, a foot candle error is huge. So the device that you get to measure light needs to be kind of corresponding to what kind of light you're going to measure. If you're going outdoors, you need to have a device that will measure to down to the 100th of foot candle pretty darn accurately because of codes and things that you need to actually measure outdoors. And for interior applications, even if it's plus minus a foot candle, it's not so bad. So there are differences in that particular meter. Another next level meter that you may or may not make use of would be something like a spectrometer. So you can tell the color of the light sources and how well they're rendering, or they're going to be rendering colors over time. If you're getting into retail lighting and displays and things like that, you may very well want one of those meters to make sure that the sources that you're getting are proper for your display. The other one would be a luminance meter, much more expensive than an illuminance meter. You point it at the source that you're trying to measure, you pull the trigger, and a luminance meter has an acceptance angle of about a half a degree of arc, if I'm not mistaken. And you point that at that source, whatever, and you get a reading in candela per meter squared, which is one of those things that we just saw back here under luminous intensity. Well, that's candela. Sorry, candela per luminance, go down to luminance, right? Now, here's the thing. The way that photometric reports and calculations describe for you the luminance of a fixture, there are guidelines out there for, say, office lighting of how much luminance a fixture should have at certain angles. And you need to figure out if the fixture you're utilizing meets those, right? Well, what they use as a basis is the area provided in the photometric report, which we'll take a look at in a little while here, divided by that intensity that comes out at that angle, or the intensity divided by the area is how that works. Now, that gets a little weird in an array of, say, 40 LEDs that are exposed for an outdoor light fixture. They'll report the area of those 40 LEDs to be, 8 inches by 8 inches or whatever. And then you divide that by the candela at the angle you're looking at, and you have a measurement of luminance. However, that's assuming that that whole area is of uniform brightness. But no, we have 40 dots in there. So what happens when you zoom in on a dot? Well, that just gets ridiculous. So there are ways to describe all these things. There are limitations in place for some of them. It's accurate for some, but some things just defy being accurately described in terms of things like brightness and whatnot. Because brightness is our personal perception of that luminance number. Right? So again, we've already utilized a receptive curve to establish candela or luminance or lumens. And yet still, when we get to luminance, we have yet more brain involved besides that response curve as to how we respond to how bright things are. So luminance gradations, if they're very confined, so if you go from 10 to 1 really quickly, you can see that. If you go to 3 to 1 and you spread that luminance brightness over a whole wall of, say, 10 feet tall or something, you might not even see a difference of 3 to 1 because our brain is not linear compared to what we're exposed to. So two different things going on there. First, the response curve for the lumens, and then our brain interpreting brightness. Our brain also interprets brightness difference based on our environment. If we're in a really bright environment, bright shit doesn't look that bad. If we're a really dark environment, bright stuff looks horrible and can blind you because we adapt across a range that's just ridiculous. I think it's almost 7 orders of magnitude we can see in, right? You can see underneath full moonlight, like 0.01 to 0.1 foot candles. You can see in full daylight in the summer, which is 10,000 foot candles. So if you go 0.01 to 0.1 to 1 to 10 to 100 to 1,000 to 10,000, that's 7 orders of magnitude our eye brain system can understand. But it differs because we adapt to parts of that brightness range for things, right? So if you're adapted to 0.01 and you shine the sun at you, I mean, you're dropping to the ground and screaming. If you're out in full sunlight and somebody throws 0.01 at you, you can't tell it's on, right? Because our eye brain system works across this huge range of values. All right. Back to that. Okay, photometry. All right, more geeky stuff here. So when we take a fixture and we want to make a photometric report or an IES file, it needs to go into a lab. It needs to be energized and stabilized so its output is not varying over time. And then what we do is we measure the output of that thing in either a full sphere, a hemisphere, or a quarter of a sphere. But we take values from straight down below that fixture up to 90 degrees vertically. If it's a symmetrical fixture like a downlight, we stop there. If it's not symmetrical in any way, then you either establish quadrilateral symmetry, or maybe you just test all the way around 360 degrees in a plan view and 0 to 90 or even 180 in a side view. And that collection of data is that IES file or that photometric report. Now that's done in a situation that makes that fixture act like a point source, right? So 25 feet is a standard testing distance for any fixture. What comes into play there later on, unfortunately, is when you try to do things like track light out of a cove, you get nowhere near 25 feet away from your fixture to describe how it outputs light. Huge difference in far field photometry versus what I just described, which is near field photometry. Very seldom do we get any kind of information in near field. So predicting light out of a cove, especially if you're trying to bounce light around, is kind of a crapshoot. Predicting light out of a downlight down on the floor as you move along, very accurate. Works out really well, right? So a little difference in the way that you collect data versus you apply that data. Yeah, okay, so think about an indirect light fixture that's built to put a lot of its light up on the ceiling in a very uniform fashion, but yet it has a little bit of a downlight to it, maybe with baffles. right? That's what this is describing when you look end on onto that long fixture. Call it linear. Right, you get on the end view, you look into that fixture, and this thing on the left that you guys are all seeing, that's you slice it through, and the big outline in the black, not the dashes, but the black, right, is the side view of that slice. So it shows you that out from the out of the long way out of the fixture, you don't get a lot of light. That's what the innermost bit of trace is there. But out the side view of the fixture, so long ways, you go 90 degrees, so we're kicking a lot of light away from this fixture up onto the ceiling. And yet we're still putting some light down. Now, the way that they described it is a little weird. So if anybody has any questions about this, please ask. But the way that the IES looks at these files is you should establish a 0-degree horizontal plane, right? And that's typically for a fixture like this at the end of the fixture. And then as you rotate around in plan view, you come to, 45, and then to 90 is straight away from the fixture. And that's what they're describing here in that black outline. That's the biggest of all these three outlines that you see, right? That's 90 degrees to the fixture. And then you come around again, and the other side should be exactly the same as the front. So that's why in this particular diagram, they're showing you three different photometric planes put into graphical form. The 90-degree one's the one that you see on the outside, sideways out of the long fixture. As you go to 45, that's the next set of lines in, and notice it gets much less candle power. You're not throwing as far as you go this way. And then when you got the end of this fixture, there's not a lot of light coming out at all compared to out the side, and that's what those dashed lines are, right? Dashed lines are at the end of the fixture, so there's still some light coming out. Notice that straight above in that graph and straight down in that graph, all of those things come together and be exactly the same. Well, that makes sense, right? If you're looking down on the fixture, it doesn't matter in 360 degrees which way you go. It's the same output. If you get underneath it and look up at it, it doesn't matter which way you're looking up at it. It's the same amount of downlight down. So all those things match up at both the 180-degree plane up top, or zenith, and the 0-degree plane straight down, called nadir, right? We'll use those terms sometimes. And then these other planes are candle power representations in between. This is really important. So does everybody understand that? Does anybody not understand that? I'm going to take silence as not, and we'll move on. All right. Now, this has completely mislabeled stuff on it. It's leaky. All right, here we go. So you imagine a lighting fixture for a roadway called a cobra head, sticks out on a post, lights up and down the road, right? So you understand that that kind of fixture wants to have a lot of its output at angles that are not straight away from the pole, right? You want to move up the road, down the road. That's what the red line is there, okay? When you take a look at a 300, well, call it 180-degree sphere of output, you find the maximum candela. Where is it most intense? Up the street and down the street. That's what the red line is, right? Notice that if I put my mouse over there, let's see here. Notice right here, right? There's that peak candle power hitting out here, and it calls it 4163 candela, right? And so what this red line represents is when you find that maximum, you go, and that maximum occurs at a plan view of, let's say 10, 20, I don't know, 28 degrees or something like that here. And then you find out also when that maximum has the vertical angle of where it is also maximum. So look at this blue thing. You climb up here and you're at about, I don't know, 70 degrees or so is where that peak happens. So if you rotate this blue thing and you look at it in plan view, it would slide from here to here as a blue line, right? Where the maximums are exactly the same value in this graph. And that would show you then that you have this really big peak both in side view and then in plan view, it spreads it out a little bit. And this looks like a roadway fixture. Okay. So maximum candela is a big deal. You find out where it is and you start to look at how then the rest of the fixture puts out its light relative to the maximum. If this fixture were instead intended for a parking lot from a perimeter, You might have a very similar blue slice, right? Where you want to kick light up way the hell out there and then bring it back. But instead of this red slice being where it's at, you might have that red coming out this way and over to the side and then coming back. So instead of throwing the light up and down the road, you then grab it and you throw it into the lot. So you might have a very similar maximum slice, but then the way that it's distributed in this plan view will be pushed over this way. Pay no attention to what they say as far as angles here. It's called the maximum cone. And notice that it occurs at 72 degrees. So this whole red thing is your 72-degree vertical plane in plan view and how it puts out light. Notice very little light behind it. Whoa, sorry about that. Very little light behind it. All the light being kicked up and down the roadway makes sense. Does everybody get that one, or does anybody not get that one? Because it's very important. I say that a lot. All right, here we go. Other ways of doing photometry. That was describing individual candela readings on a fixture placed in a goniophotometer 25 feet away. You do a whole sphere of data. You collect all those. You put them into a table. There are zonal constants for your 0 to 10, 10 to 20, 20 to 30, 30 to 40, 40. Zonal constants around the luminaire. You average your candela. You apply them times that zonal constant. You get some lumens. You can then add up all the lumens from that photometric report and get lumens. Now, if you're not so interested in the fine detail of how the light puts light out, right, with the light fixture or whatever it is, and you just want to know the sum total, there's a much easier way, right? And that's the integrating sphere. And what that does is you take a luminance meter, you shine it at a surface inside the sphere. That surface does not see any source. It's all due to bounced light. You put a reference illuminant into the sphere where you know the output of that, and you know the output of that because you've sent it off to a lab and gotten a certification that says my reference illuminant puts out 1,000 lumens. You drop that sucker in there. You take a reading. You turn that off. You turn your light on. You take a reading. You ratio the two of those, and you know how many lumens your thing puts out. In neither case does the meter see the source. It's all the light that's in that sphere just being bounced around, right? And that's an easy way to get lumens out of a fixture. So you'll see a lot of fixtures might give you a lumen rating, and you'll think, oh, well, they must have a full photometric report. Well, maybe not. Maybe they threw them into a sphere, compared it to a reference, and voila, we had 952 lumens. Because our measurement was 0.952 of what the reference 1,000 lumen source had. Now, I'm not saying those reference sources are exactly that 1,000, but they are known and they are defined, so you can do those ratios when you utilize an integrating sphere to get a lumen information back to you. Right? Now, you take all the things that we've talked about, both the individual measurements from the goniophotometer around a sphere, and maybe something involving the integrating sphere, right? And then you might also do colorimetry. We talked about having a meter that gives you the graph of the color, and all those things can be put together into a single photometric report that comes out of a lab that you can then look at to figure out whether you want to use that fixture or not. One of the things we talked about last Tuesday, and I don't know how to make things bigger for you, but I'm circling this area right here. Does anybody recognize this little band of boxes from last Tuesday? That's the color temperature at which you can call your fixture. Remember, we have this middle thing here that's the perfect, but then you got this whole box where anything in that box can be defined as, and I can't even read that thing, say 3,500 degrees Kelvin. Right. And notice this fixture was sitting kind of right in the middle, which is sort of nice. That means it's not shifting to either side of that perfect line down the middle, but they give you that information in some photometric reports that have done the color part of the tests. Some photometric reports don't do the color part. All they're interested in is candela and lumens, and it doesn't matter what, quote, the color source is, right? And you don't get that feedback. Also, parts of that report then are the candela slices like we just saw for that indoor fixture, except this is just for a fixture that has the same output in every direction. So we just have one curve and it's a big bubble. right? So it's a very diffuse sort of source. Um, Even though that fixture is pretty well near symmetric everywhere, they went ahead and did the entire investigation of angles in that middle chart, right? Where they did the horizontal angles from 0 to 337, and they did the vertical angles from 0 up to 180, right? And that's the matrix that results from all of those things that gets reported off there in the left in the polar plot. They then generate other information from that we're going to go over in terms of things like luminance and coefficient of utilization, but those are just in our short future. The far thing on the right does a little bit of calculating for you that if you put this source X feet above a plane, you can measure, you can see how many foot candles are given to you on that plane and how wide the quote beam of the fixture is. Also to be shown here in a few. All right, back to that same thing that we looked at earlier. Notice that they start showing you these candela numbers where straight down we have a certain amount, and as you start to go away from straight down, as that vertical angle increases, notice you start to get a little more. That's following that bubble, right? And then it starts to get a little less as you head up towards 90, and at 90 degrees you have no light at all. So this is indeed like a indirect direct fixture where it really ramps back on the bottom, and then the candela values up high should be greater than the ones down below, and they are, right? Because just you measure the amount of these things in this graph by how far away they are from the origin, and these little radial lines here indicate values. And notice right here, they're telling us the outermost line is 1200 candela. So we should find a peak here of just short of 1200 candela somewhere in that chart. And it looks like it happens at 115 and 90 degrees, where we get up to 1161 right there. Right. So there's a scale to these things. This is the 90-degree plane, which is this column. The little dashed line here is the 0-degree plane, which is this column. Notice when you go to the 0-degree plane in that same vertical angle, you're going to have a lot less candela. So we come down here and we go that same thing and we come in that and a lot less candela. So it matches up, right? Graphical representation of the actual values. All right. Now here's one that kind of ticks me off for this particular example is that one of the things that are looked at indoors for complying with things like RP1 from the IES and some other environment things that try to look out for people in your offices. There's several of these things out there, right? They want to look at how bright that fixture is from across the room. Well, this fixture has almost no light between 45 and 90, so that evaluation is almost meaningless because it's not going to be a problem. If you look at other fixtures like we saw, I go back, this one, right? There are some significant amount of lumens at high angles, and that's what we see off in our peripheral when we're staring at a computer screen, and that's what they're trying to limit to not give people headaches and problems with brightness from afar, right? So this particular distribution would have a lot more problems, and we'd really want to investigate how bright it is at those angles, and there are limitations for green building and other things like that as to how bright that fixture can be at those high angles, because it makes a difference as to what you see across an open office. Right. And that's why they were focusing on these angles. But for this fixture, it's kind of a mismatch. Right. Other things on a data sheet. There was that cone I talked about giving you foot candles, how far below the fixture you get, right at the center of the beam. And we'll talk about that more. Adjustment factors for color with LED land. As you go, remember when I demonstrated blue and then I put that disc on, right? So the farther away from blue you get, the less efficient it is because you have to push all that light. You have to absorb it and redirect it farther and farther away in the spectrum from blue. So blue lights, 4000K, actually have a little more light than, say, a very warm light at 2700K down here. And it's actually, it can be a significant difference. It used to be even bigger than this, but we're getting better at phosphor technology and we're shrinking that gap. But as you drive to lower and lower color temperatures, you get less and less light per watt because you're having to drive farther and farther away from the blue. Everybody get that one? Cool. Other things that you'll see about fixtures and reported either on their cut sheet or their photometric report is called spacing criteria. And what that lets you, and in a lot of cases, this is like limited to downlights. Let's just call it that, right? The spacing criteria says on this left-hand side, um, 1.1 actually says it for both. So what that means is that if you are X feet above a surface and you go 1.1 times that down the corridor or whatever area you're in, then the resulting foot candles or illuminance down on the ground or work plane, whichever you're talking about, is going to be fairly even. So that means when you're comparing downlights and you see one that has a 0.5 and you see one that has a 1.2, the 0.5 is much more like a spotlight. So if you put them at 10 feet in the air, you have to put them 5 feet on center in order for it to be uniform. Whereas the 1.2, if you put it 10 feet in the air, you can go to 12 feet apart and have it fairly uniform down on the ground. Now, that is only referring to uniformity, has nothing to do with foot candles or anything else yet, right? How uniform is the light down there? If the light is only 1 watt, you might not have enough light down there, even though it's nice and uniform. If the light is 200 watts, you might have way too much light, even though the light down there is uniform. So there's still another component to the specification that you have to get to is how much light each fixture puts out and what you were headed for. But you at least understand the difference between a 0.5 and a 1.2 is a spotlight and much more widespread. Okay. This is important. People talk about floodlights this way a lot in terms of beam angle. And then they relate that through a series of things like a NEMA distribution, where if your beam angle is within this degree to this degree, you're NEMA 1. If it's this to this, you're NEMA 2, NEMA 3. So there are ways to interpret this data into yet another form to give you an initial understanding of how a fixture puts out light, even if you don't see the curve, right? You're doing sports lighting from a really tall pole from really far away, when you get down into the skinny NEMA numbers. If you're doing it from close in and not too far up, you get a fat NEMA numbers, right? And then you can start to evaluate. Again, we'll talk about programs and stuff here in a while. But 50-degree beam intensity is what people call the beam. So if you have a lamp or a fixture or something else that says it has I'll call it a 60-degree beam, that means from straight down to 30 degrees to either side, it's taking into account both of those, right? A 60-degree beam will have its maximum candle power somewhere within that, and then its half maximum at the edges of that 60 degrees. Now, half maximum does not guarantee anything like, quote, uniform light, but it is half the candela, but it's got more distance to cover, but it's a way for us to understand where the majority of the usable light is in a fixture. They then have a field angle that's the 10% value of the max. And you know that if the field and the beam are fairly close together, you have a very tight cutoff. If you see the field and the beam very far apart, that means, yeah, there's a beam in the middle, but then all to the sides and stuff, there's still a lot of light. And fixtures are described by their beam angle. So if you're wanting to light a sign that's circular and you want to light just the sign and nothing around it, you have to have those numbers close together. Because if they're very far apart, yeah, you can light the sign good, but then all the windows and everything to either side of that sign are getting a lot of light too. Right, so that's where field and beam angle can be interpreted ahead of time a little bit before you do calculational investigations, things like that. But the important part is beam angle's 50% of max candle power, and you count it to both sides. So if you're 30 degrees away, it's 60. That's your beam, right? And field is where the 10% number is. That used to be really important with other sources we talked about last time, like those metal halide sources. I mean, you could tuck a metal halide lamp into a reflector, but then there's still the bare lamp that escapes beyond the edges. So you could have a pretty wide field angle, even though you supposedly have a spotlight. And then when you light up that sign, it is lighting up the windows to both sides and people are mad, right? So you got to think about these things. Okay, photometry visual experience. Again, photometry is just the intensity coming out. It still has to interact with the wall. It has to interact with the paint on the wall and its reflective characteristics. It needs to get it back into your eyeball. And then your eyeball has to interpret all that light coming off of those surfaces. It is not a linear relationship. So there's some experience involved in things to predict what this particular thing here looks like in actual photograph, right? Notice the photograph shows a real bright spot in the middle. This shows a dip. Well, that has to do with the angle and the distance, which we will get to in just a second. All right. Color. If you're doing things like retail, this is very important. I keep saying very important. But if you use a poor color rendering source on your nice retail goods, they're not going to sell as well. Right. Places like King Soopers and whatnot have understood that for years, and where they invest lighting, even before LEDs and all that, with good color, is in things like flowers and produce. Because a good color rendering source in flowers and produce makes those things look good and makes you want to buy them. Right? And they're high margin items. Whether you light the side of a box of macaroni really well with color, okay. But when you see that glorious orange or lime sitting there, right? Oh, I'll buy that, right? So they were even fiddling around with different light sources a long time ago when we didn't have good color rendering LEDs and the rest to highlight those particular things. So depending on the job you're doing, color can be very important or not. The thing that we lit outdoors with forever with quote white light is called metal halide. We talked about that last time. Metal halide has a color rendering index of like mid 60s. Most everything we use outdoors nowadays is 70 or above, and yet people still freak out about specifying even higher. Well, if it's worked for the last 50 years, do you really need it? If it's a car dealership, yes. If it's a parking lot, no. Why are you pushing for good better than what we've ever used before and some? Is there a reason for why you're pushing that? Think about it. Because it does make differences on how light it gets output. The higher CRI you go, the lower your efficacy. Again, trying to fill in those gaps across the spectrum from that blue source takes a little more work if you want to get even more red involved compared to everything else. And so it gets less efficient. So that was another thing I showed you on that chart a while ago. As you went away from blue, it gets less efficient. It's because of that conversion from blue to other colors. And then if you really want to saturate those other colors, same thing starts to happen. And you get this double whammy of you specify an 80 CRI 2700K something, and you're shocked to find that it puts out 30% less light than a normal color something. Well, you did two things, right? You went to the high color rendering index and you went to a low color temperature, and both of those require more energy to fill in from that blue pump, right? So that's how we relate all that stuff back to the initial fixture. And the way that this thing works is it shows you, my mouse going here, relative to a whole bunch of different colors, right? This is a new way of describing color. The old method was called CRI, color rendering index. We talked about that. CRI is an average. It was an average of, I think it was 9 pastel colors. TM30 now has 20 colors that you can compare back and forth across. So it's much more accurate than CRI ever was, because you can look at reports like this and say, well, my retail involves a lot of plants and stuff, so I need high green. And so this actually is not such a bad deal, right? Or I need more green to make my plants look better. Let's get a different LED source or something like that. And you can look through this TM30 report, you look at hue, chroma, and then the shift. They didn't do a really good job of picking something with a lot of shift. The big circle in this one right here is like the perfect illuminant. And if you can see, there's a bare little shift away from it, right? Right here, you go outside it. Right here, you go outside it. But it's a pretty good source because it conforms a lot to this. You'll see some of these where that gets a little bigger, right? And those things that are different from the source then can give a greenish hue or a pinkish hue or, some other kind of light other than just the color you're looking for if it's far away from that reference source. And what TM30 does is it allows you to look at a much more discretized version of color.
Sorry, quick question. You said the CRI had how many colors?
I think
9?
it's 9,
Okay.
12. It's
Yeah.
not a lot compared to
Okay.
TM30, right? And that's where TM30 is so much more accurate.
Okay.
CRI was okay, and it worked for a long time, but it especially didn't represent how reds were done very well. So when we
Mhm.
break the spectrum down into much more discrete versions, you can really see how much red gets taken care of, right? And you can see that a lot of sources might drop off in the red. And if you're lighting red roses, that's probably not your source,
Okay.
right? So
Awesome. Thank you.
you're welcome. It's a much more discrete version of how to tell color out of a source. All right. Oh, we're doing pretty good. So we've talked about how we interpret the energy coming off of a light source across the spectrum. We run it through the V lambda curve so we understand how people are perceiving that particular thing. We talk about being able to measure its output in a sphere or a hemisphere or something like that and give us all these candela values. When you put all that together, then you can use that information to predict how much light's going to be in a room at a particular place. And that's, in the end, a lot of what we're after is lighting people to make sure that we have enough light for a particular task or to ensure that we don't go over a certain amount of light for a particular parking lot in a particular venue, right? So the calculational portion of it now takes into account all those things we talked about and then geometry as well. And it gives us feedback as to how the light's being distributed and how much of it there is in a space. Okay. Okay. Before computers, you will all be using computers. So I'm not going to make you do these math things. Okay. You used to have to do a test and actually pass this. Not anymore. We stopped. But the manual method describes why you see what you see in these photometric reports because we used to have to do a room where we knew the fixture count, we had its photometry, we had the geometry of the room, but we didn't have a computer. So how do you figure out how much light is there? Right? It's a manual calculation. And there were ways with the photometric report to do those things, to get either average for a room or for a whole job site, and then calculate, say on a job site, the individual minimum foot candle number. And so you will then see things specified in terms of performance, outdoors at least, in terms of like something with an average to minimum of under 4-1, or an average to minimum of under 3-1. Because we used to have to go count all the poles, figure out how much lumens were dumped onto the site. That's how many lumens we had. Divide it by the site area. That was our average. And then we had to go and actually trace an individual calculation at where we thought the minimum was and manually, calculate it out. So a lot of our basis for things reported and how we do stuff is from before computers. And that's why you'll see things like average to minimum as a specification. Right. And you could do that manually, pretty, I don't want to say easily, but you could do it at your desk, right? You did not have to have anything special. IBM was not involved, right? And that's what this lumen method is. Oh, there we go. Why do we go lumen method, then point method? Point method is what I talked about, trying to get to the individual deal. And here we go with actual stuff. Now, I want you to pay more attention here. I'm going to do a little trigonometry before we get in here. I'm going to switch this way. Let's see. Stop sharing. That should get you back to my camera. And I had all these taped up, but they kept falling down. All right. Geometry review, folks. There we go. SOHCAHTOA. Sine, opposite over hypotenuse. Cosine, adjacent over hypotenuse. Tangent, opposite over adjacent. And then on this diagram at the bottom here is the most important of all, and I got to make sure you're seeing it. All right, this is the concept of parallel planes. Line drawn through, those opposite interior angles are equal. Okay, they don't do a good job of these next few slides of showing you the angle that we're really talking about. So I want you to understand this opposite interior angle thing, right? Now I get back to sharing. That one, share. All right, you guys should be seeing this very important, this very important, I can get it, thing right here. E equals I over D squared times the cosine of theta, right? This is hugely important. I keep saying that. Where E is illuminance I don't know why. It just is. E is illuminance. I is intensity. We talked about candela per square meter earlier, right? D is the distance between the source and the thing being looked at as to where we're trying to calculate our foot candle value. And then cosine theta, they completely misrepresent here because it should be on the inside. My mouse. There. See this right here? That theta sign should be on the inside of that. And that's what's called the incident angle. So if you are straight above a fixture, the incident angle, or straight above a point you're trying to calculate and you're shining straight down, the incident angle is 0 degrees. If you start to move away from straight down to that same point, you now have an incident angle increasing as you move away from that point, okay? And that is this cosine theta. I'm going to harp on cosine theta for a second. Here we go again. So share. Again, very low tech. All right. All right, so there's that formula. E equals I cos theta over D squared. There's how it works out. And notice the incident angle is the angle between straight up and where the thing is coming in, right? Very important to get that down. And to understand then, yeah, I don't know how well this is going to work. But that cosine curve, maybe I can get farther away. I've graphed the cosine curve. You don't need to see it. But when you stare at this thing right here, that cosine starts to become very important when you get closer and closer and closer to a surface, or farther and farther away from a surface, depending on which one you're talking about, right? If you're 45 degrees off, the cosine of 45 degrees is 0.707. So in addition to increasing your distance from the point that you are doing by that, you are also decreasing the amount of light that gets to the surface by 21% at 45 degrees, right? As you climb that, getting farther and farther and farther away from the source, if you get to 60 degrees, you're at half. Right? 0.5 is your cosine. So you've lost half your light when you're 60 degrees off. It gets faster and faster downhill, right? So the first 45 degrees, we only lost 21%. That means the next 45 degrees, we lose 79% of our light until you're parallel to the surface and you get none because the cosine of 90 is 0. Right? And where this really comes into play a lot is like when you're trying to graze a surface and you're trying to calculate that graze. Well, at the bottom of a 10-foot wall, when you're a foot or a foot and a half off, that angle of incidence from straight out from the surface back to the fixture you're talking about gets to be like 70, 80 degrees. And the cosines of those are down in the 0.1 or 0.2 range. So you've lost 80% of calculated light when you get down to those very grazing kind of angles. You get back up high on that same wall and you'll see values rise tremendously depending on what your distribution is because your D squared gets really low and your cosine value starts to get more rational, right? So this direct method of calculation tells us that when we look at values on, say, a wall that we're grazing, they don't mean a lot because they show almost nothing way down low. Now, if you have a textured wall, what happens then is instead of that surface being parallel and your incident angle coming in, very high, well, now there's little bits of paint that might come down and change that incident angle to almost direct on. And those little bits of paint will come back to your eyeball. And so you can actually see light at the bottom of a graze that you wouldn't otherwise. If you have a non-textured wall, if it's a mirror or if it's very smooth, you might not get that return. And trying to graze a wall like that might not do you much good. You can't graze glass. None of it comes back to you, right? You can't light glass and have it come back to you. It's just a bad idea in the first place. And yet I've seen people try to light buildings that are mostly glass from the outside. Doesn't make a lot of sense. The guys flying over in the airplane see the bounce off the glass. Nobody else sees a return. Why are you doing that? Figure out another thing, right? So this cosine angle is supremely important in that calculational engine right there, where illuminance is equal to the intensity of our source divided by the distance between our source and the point we're measuring squared. times the cosine of the angle that we're coming in on, right? Again, that theta on their little descriptor right there should be on the inside of where it says perpendicular and D, because that's the thing that we're interested in. They did do the top part right. And so if we go back to our opposite interior angles, you understand that the theta they're talking about up top there is the same theta as down below that we call incident angle, which forms that E equals I over D squared times cosine theta, right? A lot of time spent on that, but it'll allow you to evaluate things a lot easier if you understand those relationships. All right, let's come back over here. I'm still sharing the right screen, right? You guys are seeing inverse square law? Or are you watching me?
We're
No, we're
seeing
watching you.
You're watching me? All right.
Yeah.
Shit. Pardon me. Let me go back to that one. Share. Okay, this whole time I've been circling this silly formula down here, right? You guys see my cursor now going around the formula?
Yep.
All right. Big deal, right? If you're straight above it, this cosine theta goes to 1. If you're 90 degrees from it, it goes to 0. You cannot light something parallel to it, period. Because there is no cosine left for you to bounce anything back to your light unless it's textured. And if it's textured, now you got little bits that might send light back to you. So you have to think about those things, right? All right. We talked about cosine, sine. Cosine is the big one because it's part of that formula, and it describes how light drops off relative to your surface when you're farther and farther away from straight onto it. They do the same thing here with that theta thing. Angle of attack. It's called angle of incidence, or your incident angle, and that's the angle between what they call here perpendicular and the way that your light is coming in. That little theta symbol should be between the D and the perpendicular. All right. So they pull a little math trick here to make vertical surface calculations maybe easier for you, but at this level, don't pay attention, right? To the man behind the curtain. Keep in mind your incident angle and everything else, and you'll be able to do it just like a horizontal surface. They try to take a shortcut by switching you to sine instead of cosine. It's confusing as all get out, and I would not recommend looking at it that way. If you always understand that you have a surface perpendicular to that surface, and then whatever angle you are off of perpendicular is your incident angle, and that then applies back to that whole ID squared cosine sort of deal. Right? They show you different ways to do this here. One of the most easiest things, and something that I actually use fairly often, right, is you come over to number 3 here. Remember I talked about when you're directly over a point, that cosine value goes to 1, right? So now all you're left with in that calculation is illuminance equals intensity divided by distance squared. So if you have a downlight, you have 1,200 candela coming out of that downlight, and you put it at 10 feet above a floor. E equals I, 1,200, divided by D squared, 100 in this case. So you have 12 foot candles straight below a fixture. And 12 foot candles, pretty good number for a corridor. Throw a light loss factor on there, maybe it's 10. Talk about your spacing criteria that we saw earlier that said those downlights have a spacing criteria of 0.9 to 1. So now if you put those suckers 9 feet on center, you'll have a fairly uniform thing down below with straight below a fixture having at least your 10-foot candles, if not a little more from the adjacent stuff, right? And that's all mental without doing a calculation yet. You just have to look at the intensity values or an IES file or something from the manufacturer of that particular fixture, and you can do some of this stuff like straight away without ever going into your computer. If you do that same counting process and the fixture let's just be ridiculous, had a 20,000 candela number, and you put it 10 feet above a floor, 20,000 divided by 100 is 200 foot candles. Maybe that's good for some sort of production or tiny silversmithing, but it's probably not good for a corridor. And so you'd know to kick the 20,000 candela fixture out. So this point method, E equals I cosine theta over D squared, can be employed really easily in some instances, and it gets complicated in others. Like if you have to go into an outdoor file and figure out your angles to what you think in that parking lot is your minimum, and then interpret the data and come back and do calcs. It can be a little onerous, right? But we have computers that do that for us now. So what I want you to really understand then is this concept of incident angle. If you're straight on at zero, if you move away, it starts to go. If you get beyond 45 degrees, you're below 70%. And even more and more and more and more and more as you get farther out. And that's why in parking lots, you see fixtures that have peak candle powers up in the 60, 70 degree range because they're trying to overcome both D squared, which is super important. I keep saying that, and the cosine angle. When you're way the hell out there with an incident angle of 80 degrees, what is that, 0.1 or something is a cosine? That's something I wanted to tell you all. You might not do much of this cosine stuff anymore, but within your grasp, if you have an iPhone, if you have the regular calculator on your iPhone and you turn it sideways, you get access to cosine, tangent, sine functions, and you can type in an angle and hit cosine, and it'll tell you what it is. You can type in second function, your cosine value, it'll tell you what angle it was. So you even have this right in your little hands anytime you want to do cosine stuff, right? Mine wasn't working earlier. I had to figure out why when I turned it sideways, it didn't work. Um, Rebooting was the answer. Let's see. Uh-huh. And again, you used to have to take tests. I'm not going to make you, right? This one's pretty easy. If we have a fixture straight above, that means cosine's 1. E equals I over D squared. In this case, I is 3,000 candela. D is 7. So 3,000 divided by 49 is your answer for foot candles. Go back to there. So that gives you 61 foot candles straight below that fixture initial. All right, everybody see how that worked? All right, that's the easy part of that E equals I cosine theta over D squared because cosine goes away, becomes 1 when you're straight on to something. And what they try to demonstrate in these things now is how the cosine angle and the distance change your answers for a particular fixture, right? I am not going to make you go through the math. But notice where it says 30 degrees, if we remember alternate interior angles are equal to two parallel planes, the incident angle down below, which is what they should be more concerned about, from that surface straight up over to where the eye comes in is 30 degrees. Right? So they keep putting the numbers in places where it doesn't matter much. 30 degrees is the incident angle. 30 degrees in this case is also where you'd go in the candela chart to pull your candela I value if it were like a symmetrical downlight. You look where 30 degrees up is, you get that. Now you have an 8-foot distance, you have a 30-foot or a 30-degree cosine involved, and away you go. Right? Let's go back here. And then they try to pull that sine thing on you. Don't worry about it. Just reverse things. Now here they actually did the nice job of drawing in the 2 dotted blue lines to where you know your incident angle on that wall is above the 8-foot and between the 8-foot and the blue line. That's your incident angle. Then you have to find what your candela is. It says 3,000 candela. And we could actually do this one if we did E equals I, which was 3,000, divided by the distance squared. Let's see here, 3,000 divided by 8, divided by 8. And then the incident angle, which they didn't show you up above, is 30 degrees. So times the cosine of 30 times 30. Oops, wait, hold on. Let me do that again. Sideways. 30 cosine is 0.86. Makes sense because 45 is 0.707, right? So that's your cosine value times your intensity, 3,000 candela. And then divided by the distance squared, which is 49, or I'm sorry, 64. And we get 40 foot candles on that surface. right? It's just all an application of that very simple formula, but you have to understand which parts of it you're looking at, what the incident angle is, and the rest. All right. Here's examples that you'll see given, especially in track heads, right? Where they've done the work for you ahead of time with that I and D and squared and all that other cool stuff, right? Where they show you straight below the fixture, cosine equals 1, right? Is basically I over D squared. Put it on the right screen, Bob. Right here, directly below it, right? You'll get all these foot candle numbers that are basically intensity divided by distance squared. When you start to invoke angles of aiming for horizontal foot candles, right? Well, now you're going to have a cosine of 30 involved and you're going to have a bigger distance. So all these values are going to be less than the values in the direct. And then when they come over here, 30 degrees aiming, now they switch their plane of reference to the wall. So now the incident angle is 60. So they're starting to use 60 cosines for this guy and distances squared. And then this one where 60-degree aiming angle to the vertical. Well, now that's a 30-degree incident angle on the wall. And now you're using cosine of 30 instead of cosine of 60. So these should rise relative to these. And they do, right? So it all works out. But they've done the math for you ahead of time and you get an idea of what you might be able to cover. When they talk about length and width, in those, they're talking about where that 50-degree beam extends to. There's still light beyond that, but the kind of usable light, if you call it within the beam, which is not the same at the edge as it is at the center, but it's kind of our usable light level, that's what they refer to as L and W in those things, right? Length and width of the pattern on the wall. All right, let's see where we're at. 646. Point method review. E equals I over D squared cos theta. That's the big deal. Always remember that theta refers to your incident angle to the surface, right? Incident angle straight onto the surface is 0. Your cosine becomes 1, and you have no cosine depreciation. As you move away from that, your distance gets longer and your cosine values drop, and so you fall off in terms of how many foot candles make it to that surface from that same fixture. Right? That's a big deal there. All right. Now, lumen method is a thing that some computer programs still use and another manual way of going about figuring out a room and number of fixtures and averages and things, right? Again, you will not have to do this on your own, but it's cool to understand the parts of it because you can then interpret photometric reports and understand how the fixture, say, puts out light. The way that this lumen method works is you have a work plane, a luminaire plane inside your room, and you describe the ratio of the room area to the room length and width, okay? And then that is involved with the IES file to produce a coefficient of utilization table. That CU table is then used along with how many fixtures and lamps you have in the room, divided by the area to give you how many, say, average foot candles you get. And what coefficient of utilization means, how much light leaving the fixture in your particular geometry is going to make it to the floor. The geometry also involves reflectance values in the room. So you will find that those CU values drop when you paint your walls black. We talked about that earlier in people's perceptions of brightness, right? That value will rise if you paint your walls white for the same geometry of space. And you need to understand then the different geometries of space will bounce light more efficiently or less efficiently. If you have a gigantic open warehouse, almost all the light from the lights up above are going to reach the work plane because there's not much wall involvement in a gigantic open warehouse. If you're in a grain silo, right? Extreme example, right? Light at the top isn't going to make it down to the bottom very well if it's hitting the walls first. You need more of a spotlight involved now, whereas in the big open warehouse, it almost didn't matter. So now in the silo condition, the walls matter a lot as to how much light finally makes it down because you're going to be bouncing a lot of light off of them, right? Multiple times to try to get to the base of that. And you'll see that reflected in these tables. It's a pretty simple concept, right? How many lumens do you have? On this, I'm going on the right-hand side here, okay? So that phi total used to be referred to as number of lumens per lamp times number of lamps per fixture times number of fixtures in your space, right? That gave you a count of source lumens. You apply a light loss factor, and then this CU table I talked about, how does the fixture emit light, and how does that interact with different geometries of the space? Now you've got a count of lumens, you divide it by the area, voila, you have your average. Again, we're using computer programs to do a lot of this now, but this is how it comes together. And some of these parts need to be part of your computer program input, especially that light loss factor. Okay. There are limitations to the method, right? You're supposed to be within a 1.6 to 1 ratio of length to width. It assumes everything is tissue paper walls, right? Not mirrors or glass or any other kind of stuff, right? One luminaire type spread evenly throughout the space. But you could do it at your desk, right? Without a computer. I talked about dimensions. Oh, and here's a good example of that stuff, right? So the room cavity ratio, in the second thing, oh, here it is. Here's that room cavity, right? So the room cavity ratio refers to the height, the length, and the width of the room in this formula. 5 times the height times the length plus width divided by the length times width. And what that works out to mean is the taller and more like a silo your space is, the higher the room cavity ratio. The long and flat and big open thing like your warehouse is a lower room cavity ratio. And then when you come to, oh, where are you? And then when you come to the chart, this is swinky. And you go and you start at numbers that are high. As you climb that room cavity ratio number, notice they go lower and lower and lower. And that depends all on the fixture and its distribution and how it interacts with your space. Notice the walls at 70% have a higher number than the walls at 10%, but not when it's super flat. Walls don't matter when it's super flat, but you get down to where walls do matter when you're into more of a silo. Notice you lose like, I don't know, a third of your light to the walls because the walls are more important in that silo than they are in your warehouse. So these charts give you an idea then of how the fixture is employed. Right? Room cavity ratio, we just did that. There's the cube or silo on the left, the warehouse on the right. Again, I'm not going to make you do the math. Ooh, and this is where then, if you're in the silo, if your walls are still the dark brick stained by soot versus cleaning them and painting them white, right? That's where that reflectance value in those charts made a big difference. And then common values for reflectance of stuff. I have people ask me a fair amount of time to say light a lobby or an entry space for a school or something like that off of their beautiful wood ceilings. They don't want any direct light. We just want to light it off. I say, okay, you can. But if you look over here on this chart, notice that wood light at the top end, right, is 35% reflective. Ceiling tiles are 80. So most of our calculations for things in commercial spaces involve ceiling tiles and whatnot. So you got an 80% ceiling. You get into wood and the light wood is 35%. So if you want to bounce light off that, it's going to take you 2.5 times the amount of energy to bounce light off of a 35% ceiling than an 80 to get back down to light whatever it is you're trying to light. So I say in a lot of cases, let's light your beautiful wood ceiling so you can see it. But let's use something that's more a little efficient to make sure that you've got your X foot candles down below that. Right? Because of this reflectance value. Anything else I want to point out? Brick, 30%. Oh, white paint on tile, 70%. We use actual tiles being 80 for most of the time. There are some manufacturers of ceiling systems that tout the fact that their ceiling panels are even more reflective or efficient than that. Sometimes they go specular, and that can be bad if you're indirectly lighting because now you see stripes and stuff on the ceiling. So things to think about when you're bouncing light around a room. What are the surfaces? How are we going to see that when it's finally done? Because illuminance light onto a surface is one thing, but light coming off of that surface is what we actually see. So you kind of have to blend those things together. Okay, spotlight versus not spotlight. Notice when you get down very low in the room cavity ratio, not spotlights at 72, spotlights at 88. Spotlight's not interacting with the walls as much. So you get more light making it down to the work plane with a spotlight than you do with the other one, right? That's the point of understanding of these tables, not necessarily the individual angles. Okay, and we talked about going low on the reflectance instead of high. That affects things a lot. Big example. So one of the things I had my calculator program for when I took classes was to put in the 4 numbers around the actual one I needed. So if my room cavity ratio was 3.3 and my wall reflectance was 20%, how do you come up with, is that going to be probably 0.87 or something? You can guess. But I had a little formula done where you plugged in the 89, 85, 82, and 77, and it gave you your answer. That was kind of handy. For doing the hand calcs that we were required to do to get a good grade, you guys are going to use computer programs. Remember that. Now this, with all the easiness that computer programs gives us and all the not hand doing we're doing, right? This still needs to be taken into account when you do your computer program. How fast does the light depreciate? Or nowadays, that concept, we used to have life ratings for lamps, right? And when you threw 100 lamps into a room and half of them were burned out, you figured out how much light the remaining ones were putting out, and that's what you called life rating when they're half burned out, and then what their lamp lumen depreciation was at that point. LEDs don't act like that. LEDs hang out all together, and very few of them actually fail, right? So when you deploy those same LEDs in different fixtures, every fixture has a different lumen depreciation curve. We used to be able to use the same one for a fluorescent lamp, and no matter what fixture it was. Now that is not the case. Got to look at your individual fixtures and their performance information to figure out how they depreciate, and then you, as the designer, need to come up with how far in the future then am I looking to predict my results. Had a fellow who lit a lot of parking garages with metal halide lamps back in the day. He knew that metal halide depreciated about 50% before it burned out. So he did all of his designs based on safety and security, such that when all the fixtures were at 50%, he was meeting his required values. Well, that means day one, he's doubling the energy he needs for that whole time. And this is where lamp lumen depreciation really comes into play, and understanding how things depreciate over time and where in time you're going to look at for this depreciated number. Lots of planners want to see initial because it's easy. But if it's initial and you've got a very good maintained fixture, a very shitty one, 50,000 hours down the road, the not so good one, sorry, must edit, could be down to 70% output while the good one's still at 95. Well, you as an engineer or designer probably need to do what that guy with the garage did and design to the 70% number as your minimum so that you're always meeting your values, right? If you accept a substitution that goes from the good one to a bad one, you might need to increase the wattage of that fixture to overcome that lumen depreciation over time. Right. So it's kind of important to understand how a fixture depreciates over time, right? Not only the source itself, but then what kind of environment is it in, and what kind of lensing does it have, and how does it collect dirt? Because, here's a horrible example. One of the places I went to work with to start, still allowed smoking in the office. And we had linear indirect light fixtures. When that fellow left after I was there for a year or so, we went up to clean those light fixtures, and they were disgusting. They had nasty brown shit on the lenses that took us a couple of passes with Windex and stuff to get off. And when we got done, I don't know what the percentage was, but the amount of light that we got back into our space was significant because that luminaire had gotten dirty and it was not putting out how much light it was supposed to because of the dirt, smoke, whatever was accumulated on the lens. So you go into industrial environments, you need to account for that, right? You go into an office has filtered air and gets cleaned a lot. Well, it's probably not going to get very dirty unless you got a bunch of smokers in the room, right? But we don't have that anymore, so you don't need to worry. So things to think about in your application, right? Then room surface dirt, same thing. If you're bouncing a lot of light off the ceiling and the walls, if you're in an area where you're right next to the highway, that might actually come into play over time because your room surfaces might get dirty and reflect less. And if you're counting on them to be your light source and reflect, well, you should probably take that into account. When it comes to old school calcs, the next thing down below, non-recoverable factors, talks about a ballast factor. And we talked about those last week for fluorescent fixtures, where a lot of times that ballast factor for a standard ballast was about 0.88. So another 12% of your lumens are gone for your calculation. Or if you need to replace something, you don't need to replace those 12%, right? Because now we don't have ballast factors involved in our stuff anymore, right? But we used to have to take that into account. All right, where are we at? Next. There we go. Oh. All right. We talked about room cavity ratios. We talked about our light loss factors, both luminaire dirt, room surface dirt, and lamp lumen depreciation. This number's gotten quite small, lamp lumen depreciation, depending on when you decide to do your calcs. We used to have a standard one for everything, and now it's all different. So you have to pick a spot in time and figure that out, right? Examples, fundamental concepts, luminous flux divided by area is illuminance. We talk about room cavity ratios, silos versus warehouses, and how different fixtures react in those. Light loss factors, don't forget them. A lot of people just default to a 0.9. Well, actually, it's not so far off if you got LEDs that don't depreciate much and you throw in a little bit of room surface dirt and a little bit of luminaire dirt, right? It can work. Modeling. This is what you guys are going to be doing. Maybe not making fancy renderings like that, but you're surely going to get into either utilities or full programs where you describe the space, the fixtures, and then the calculational plane, and it gives you answers. Okay. And then those things can be taken up into renderings as well. So here's the real basic one. It goes back to that lumen method we talked about, where one fixture type in a room spread out evenly to an average value. And you pick a fixture, you give it the inputs, and it gives you an answer. You don't like the answer, you can start to change stuff. Excuse me. Note for this particular example, they made a 20 by 20 by 10-foot room. They wanted it to answer the thing it put in was, what does 30-foot candles, what does it take to get to 30-foot candles, right? They give you an answer. They give you 16 fixtures. They give you a watts per square foot for the fixture, right? But then notice the spacing they give you. 5 foot by 5 feet. Well, it's accurate. If you wanted to get 30-foot candles with the fixture that they picked to start this with, that's what you'd have to do. Who in the world is going to put light fixtures into an office or a classroom at 5 by 5? That's a bad answer. So you have to interpret the results that come back out of these utilities and say, well, it's not going to work. So I need to increase my output to get me back to spacing so they're getting closer to what's realistic, right? Or you could put in the spacing with this fixture and get the answer of, let's see what, 8 by 8 be 64 and 25, almost 3 times. You get an answer of, say, 13 foot candles with this fixture on 8 by 8 spacings. You'd be like, oh, well, that doesn't work. Right. And then you go back in and you start to fix, right? And you look and you fix and you look and you fix and you look until you get something that resembles a real answer that you can utilize in your either design or application. Then the programs get even better and better and better in terms of computing individual illuminance points, as well as then taking those calculational results and other information that you give the program, like wall reflectances and things. And then you can generate renderings from some of these programs. Now, those renderings can be helpful, but they can also be misleading. Right? You render your room in all gray, 80, 50, 20, it looks one way. They come in and do the dark wood paneling and things like that, and then it changes everything entirely. Some programs can handle some of that, some can't. One of my compatriots spent an hour trying to get the wallpaper background on a particular rendering right. So they can be very, very time intensive compared to just calculations. So to do renderings right can be quite a onerous task. I just want to put it out there. Don't think that it's just as easy as pushing the render button to get things right. There we go. It can actually look out pretty good. And notice in this particular example, somebody went in here and built in this curtain pattern, right? They picked this slightly greenish color instead of a gray for the wall, right? They did a wood applique something onto each one of these panels. They had to do a different color and a surface for this countertop, right? So you can start to see how much work can go into generator or rendering. So what is the rendering to be used for, and how much work do you need to put into it to make it usable, right? Would be my comments on renderings. Nice ray trace over here to even show shadows from the sunshine, right? And then here's what I was talking about, just like an 80-50-20, look at where light is in a gray room. I use that to convince one of my coworkers to put some downlights over his sink in his new kitchen. Um, Another detailed analyses from dimensions. Horizontal, vertical points. I think that's covered a lot of that. Oh, and then, like I mentioned, the guy who did parking garages, he actually went out and did foot candle readings in a grid to get a true average. Right? It's very hard to find an average in a space by measuring if you don't lay out a very good grid of points. And so that's why IES has moved in many cases from what we talked about earlier as like outdoors, an average to minimum ratio, because we could count fixtures, times them by their lumens, divided by the area, and quote, get an average. Well, now they've kind of gone to a more sophisticated way of doing, say, maximum to minimum foot candles. And when you can do 1,000 points across the site, it's pretty easy to pick out the max and the min and see what kind of ratios you got going on. It's even easier maybe at night with a meter to walk out there, find the brightest spot and measure it, go to the darkest spot and measure it and find out what's going on, right? Without having to lay out an entire grid for the entire something to figure out your average, right? You can do max to mins. So lots of new recommendations for outdoor stuff you'll find are in max to min. Makes it a lot easier to do that. We have programs to calculate all the points to get there. So it works pretty well, but we still have the institutional memory of averages that were easier to calculate via the lumen method that we saw here today and the coefficient of utilization and all that. And same thing for outdoors, right? You could get an average that kind of way, and then you could work your way back into something approaching uniformity. Now we use the computer to do all the points to do that stuff. But it's good to understand why were they telling me what average to min is? Well, that's why, right? Because it was easier to calculate that way. And they knew that a parking lot that was done to an average to min, or roadways for the most part, 4-to-1 average to min, slower roadways, you get the faster stuff in highways. They went to a 3-to-1 average to min, that kind of stuff. Meters. I talked about these earlier and I thought they were pictured then. Here is an example over here on the right-hand side of illuminance meters. Minolta makes very nice illuminance meters. There are a bunch of other companies that make them as well. We have field techs who use a meter that I don't know exactly where they got it, but it seemed to do a really good job. And it was like a third the cost of these guys. But they're doing a lot of indoor stuff, not outdoor. If you're going to do outdoor, remember, you got to be more accurate. Color spectrometer, again, doing a lot of retail work. You might really want to understand how that source puts out color relative to your products. And then the luminance meter, right? These things cost about 3 or 4 times what a nice illuminance meter costs. So I've never had one, but I have been able to borrow one a few times. And you can go and you point the thing at a source and it has like a 1/2 degree acceptance angle. And it tells you then in a readout what the intensity of that thing you pointed at is in terms of candela per square foot or square meter. Right. That will be a thing that can then do what photometry does. If you go out and look at an array of 80 LEDs, if you can get back far enough to get them all in that little 1/2 degree angle, then you can actually get a reasonable idea of what the photometric report and then the meter would match up to say. You get closer and you look at one diode and the numbers go through the roof. So you get people say, well, you can't do anything over this candela per meter squared. I'm like, well, that outlaws everything that we use. Because if I actually look at a little chip on that 80 chip array, its luminance is a hell of a lot more than what you're saying is allowed. If I average all 80 over the area, why then I might start to be talking your language. But all that's ignored. Same thing happens indoors. When you have a 2x2 and you've got a center stripe of LEDs and a little basket underneath it or something, all the light's really concentrated in that stripe. But the report counts the whole 2x2 area as the area for the intensity to be divided by to see if you can pass the lead or the green building or the IES FOL or whatever their restrictions are at those certain angles that we talked about earlier, 55, 65, 75, right? So there's a little bit of mathematical gyrations that go on that don't really represent reality, and yet you have to comply with because you're in a situation where those things are part of the parameters of your project. Those 6 key quantities, remember those guys? I'm going to go back to them because they're just super important, and I keep saying that. What's there? There they are. If nothing else, take a screenshot of that, keep it at your bedside, well, not your bedside, but maybe your work table, so that if you ever have to interpret back and forth between things that you're reading in photometric reports or information that people are giving you about products, you understand their relationships, right? And luminous intensity should say candela per steradian, if you remember my whole concept of 4 pi steradians of solid angle, and that a item with an intensity of 1 candela into in all directions, right, would have about 12 lumens, right? So you can almost talk about candela versus lumens in a very particular sense, but that's a very particular sense. All right, I'm going to stop sharing. Maybe. Anybody have any questions? Or if I thoroughly bored you?
Definitely not bored.
Okay, good. No questions? In which case, we're done. And I wish you all a fine evening.
Amazing. That was
Thank
great.
you.
so much.
Thank you so much.
Good stuff. Thank you.
You're
Thank you
very
so
welcome.
much.
Thank you very, very much.
You guys all have a good night.
You too.
Yeah,
Bye.
you too.
Thank you.